office now.
Yes, sir.
Yeah, just send it to me. Okay, guys, let's start. You know, last time we started the new chapter. Let me just revise the things because a couple guys were not here last time. So let me just go through this one very quickly. We almost finished Article 5, not 5.1, but half of Article 5.1. And let me start from the beginning. So look at over here. It says the graphical exploration of the vectors, the transformation of Cartesian plane. That means whenever we write the vector, suppose we write ax equal to b. So ax equal to b, and usually this is the matrix equation, ax equal to b. And where a is the coefficient matrix, x is the matrix of unknown, and b is our column vector right inside. But guys, please look at over here. This matrix actually, what does it represent actually? It actually represents a transformation. So far, we just worked with we just played with the numbers, and we just found the unknown vector x, unknown matrix X, but we did not take care of the graphical exploration. I mean to say that we have not seen any kind of graph, what your vector A, matrix A, or whatever B or AX, some matrix is multiplied by your matrix A. What does it represent? We don't know this thing. So in this chapter, and probably in the next chapter too, we are going to explore this graphical representation of the multiplication of two matrices. In short, just keep in mind this thing that whenever you have a matrix A, this matrix A is nothing but a transformation. It actually transforms your given vector to some other form. As per example, suppose I give you some square lines, and suppose that square lines is making one square on your x and y plane. And if you apply some transformation, so that plane or that, that square lines, 4 lines which make a square, after the transformation or after multiplying by a matrix, both are the same thing. Please keep in mind this. Once I say the no voice, please. Please. So once you have 4 lines which make a square, and that square is supposed transformed to some parallelogram, quadrilateral, like this, because lines are always transformed to lines. Lines cannot be transformed to curves, but curves are always transformed to curves, or sometimes lines too. So please keep this in mind. And whenever you are talking about a transformation, it is nothing but that some vector is multiplied by the given matrix. So matrix A, whatever we have been doing since long time, that matrix A actually works as a transformation. It works as a transformation. It transforms your given figure into some other figure. So that's what we are going to see over here. Look at here. In the transformation of a Cartesian plane, just x and y plane. So we studied, what is this? Yeah, we studied in chapter 2 or section 2.3 in particular, how to visualize vectors and how certain types of matrix arithmetic operations can be graphically represented. We limited our understanding of matrix multiplication to graphing a vector, multiplying it by matrix, then graphing the resulting vector. In this section, we will explore these multiplication ideas in greater depth. Instead of multiplying individual vector by a matrix, see, we just multiplied one individual vector by a matrix. Your matrix A, suppose 2 by 2 or 3 by 3 and one vector, x1, x2, x3. So instead of multiplying individual vectors by matrix A, we will study here what happened when we multiply every vector. Every vector, I mean to say, just not one vector, but 1, 2, 3, all column vectors, all together, not one by one, in Cartesian plane by A. So that's what we are going to see, that what will happen that when we multiply every vector, all column vectors at a time with your matrix A. Suppose you have 3 by 3 matrix and you have that column vector also 3 by 3. So one column, second column, third column. So we are going to take multiplication of two matrices. Suppose A is one matrix given and B is another matrix. So we are going to multiply these two matrices and try to see the transformation, what type of figure it takes. Okay, because of the distributive property, Cartesian plane will be transformed in a very nice predictable way. Some tools are there. Straight line will be transformed into another straight line. They won't become curve or jagged or broken line or like this. So once you have straight line, it would be in some other figure. But suppose you have squares, 4 straight lines represent a square. then you may have, after transformation, you are not going to get some curvature. No, it would be some lines, but it could not be always a square. It could be a square, but not always. It could be a rectangle. It could be a quadrilateral. It could be a rhombus. It could be some quadrilateral, rhombus, something like that, right? So it could be anything, but it is in the form of the straight line. So straight line will always be transformed into other straight lines. They won't become the curvature or broken line like this. The lines will be transformed into other curves. See, straight line will be transformed into other straight lines. So straight line will be transformed to others, but curves will be transformed to another curves lines. So line to line, curve to curve. Perhaps the curve will become straight line, but curve sometimes becomes straight line too, but it won't become jagged or broken line. So straight line, if you have straight line after your multiplication, that matrix in the form of straight line, suppose some column vectors are given in the form of straight lines, and if you multiply that one by matrix, that straight line will be transformed to straight line. Straight line, why we have straight line will be transformed to straight line. And suppose you have a curve, the curve will be transformed to a curve, but sometimes your curvature may be transformed to some straight line, but it won't be any kind of jagged or broken line. Some curvature may be straight line. So please keep in mind this thing, the curve to curve, but sometimes curvature to straight line too. Okay. One way of studying how the whole Cartesian plane is affected by multiplying by a matrix A is to study how the unit square is affected. Unit square means always we start like this. You can look at over here, 0, 0, 1, 0, 1, 1, and 0, 1. So we are moving in the anti-clockwise direction. So one way of studying how the whole Cartesian plane is affected by multiplication by a matrix A is to study how the unit vector is affected. The unit vector is in the form like this, 0, 0, 1, 0. So 0, 0, 1, 0, 1, 1, and 0, 0. Each corner is represented by a vector. So that means here 0, 0, and this corner here to here, this is one vector. Here to here, this is another vector. Here to here, third vector. Here to here, fourth vector, like this. So represented by a vector. Each corner represented by the vector that points on it. Multiply each of these vectors by A. So each of these vectors means this vector 0, 0. These are the vectors 0, 0, 1, 0. So all these four vectors are multiplied by our matrix A. And we can get the idea how A affects the whole Cartesian plane. Look at this example. This will give you a very clear idea. Plot the vector of a unit square. Unit square means this one, 0, 0, 1, 0, 1, 1, and 0, 1. Before and after they have been multiplied by A. So before we multiplied by A, what will happen? And after we multiply all these four vectors by A, what will happen? So before we multiply, just the same figure, 0, 0, 1, 0, 1, 1, and 0, 1. This will be the figure on the previous page. Look at over here. After multiplication, what will happen? So whatever the vectors, whatever the points I have, as I told you, these points are nothing but the vectors. So let me write these 4 points in the form of the vector. So my first vector, sorry. What's wrong with this? You want my arrow? Why I'm not getting my arrow? See some. Okay. So vector is given to us like this, 1, 2, 3, 4. You know that we have been working with the same matrix since the last chapter, also last 3, 4 articles. So 1, 2, 3, 4. And 4 vectors are in this form. So let me multiply with each of these vectors by a given matrix. So first matrix, 1, 2, 3, 4, this vector 0, 0, it will give us 0, 0. And this matrix multiplication is quite possible. This is 2 by 2, this is 2 by 1. So number of rows over here, that is equal to number of columns over here. So multiplication is possible. Here you can see 1, 2, 3, and 4 given matrix, and 1 and 1 multiplication is 1, 2. Here it is 5 and 5, and here it is 4 and 3. Now if you plot this 0, 0 on your graph paper, so 0, 0 will be the origin. And then after, if you plot this 1 and 2, so 1 on x-axis and 2 on y-axis, so 1 and 2, that will be of this form. To get over here, 0, 0 over here, and 1 and 2, that will be over here. And then after we go for 5 and 5. and then 4 and 3. So 5 and 5 will be over here. See here, x-axis 5 and here y 5, and then 4 and 3, that will be over here. The best things to visualize over here is, you can see here we were moving anti-clockwise, and here the figure is transformed by this transformation by this matrix A. The figure is transformed to clockwise direction. The straight lines are converted to straight lines. Here it is 0, 0. Here it is this one. That means, look at over here, we moved from here to here, and then here to here. That means now we are moving in clockwise direction. Then here to here, and then here to here. So it depends on the nature of the matrix, which matrix you are taking, and or which transformations you are taking, that transforms your given figure into some other figure. Here the square is transformed to some parallelogram, you can see over here. Okay, so how the square got turned into some sort of quadrilateral, or you can say parallelogram. How the triangle and the square vertices seem to have changed places. This we are going to see next. And how straight lines are transformed into straight lines. Straight lines are being transformed to the straight lines. Okay, so look at here, guys. Here what we do, what we are doing over here, look at here. Here I didn't have color pencil, so that's why I just did like this. This is my red dot. Suppose this is my red dot. These two are red dots. These two are red. This red dot over here between two vectors, 0, 0 and 1, 0. So halfway is my red dot. Here I have two red dots. So how these red dots would be transformed here? You know that this vector is transformed over here. So my red dot would be like somewhere over here. Anyway, look at here. Okay, here the unit square has some additional points drawn on it, which corresponds to the shaded dots on the transformed parallelogram. So this dotted line, this highlighted black line that is over here, look at here. The unit square has some additional points drawn on it, which corresponds to the shaded dots on the transformed parallelogram. Not how relative distance are also preserved. The relative distance are also preserved. That is, whatever distance you have, that distance is preserved over here. Then the dot halfway between the black and the square dots, the dot halfway between the black and square dots. This is this black and this is square dots. Square dots is transformed to a position along a line. Is transformed to a position along a line. Halfway between. So this dot that is halfway between, somewhere over here, halfway between the black and the square dot. So this is the black and this is the square dot. So this is the halfway. So this one that is transformed over here. Same way, if you move like this, so this one, sorry. So this one, these two red dots, they are transformed over here. These two red dots are transformed here, here and here, here and here. Okay. Plot the transformed unit vector. Plot the transformed unit vector after it has been transformed by A. After it has been transformed by A. See here, plot a transformed unit vector. Unit vector means 0, 0, 1, 0, 1, 1, 0, 1. So multiply this one by the given matrix. So let me say this one, my matrix B, unit square as a matrix B. This is my matrix A. Let me take A into B. A into B resulting matrix is this one. 0, 0, 0, 1, negative 1, 0, no, negative 1, 1, and negative 1, 0. Negative 1, 1, and negative 1, 0. Okay. So this is naturally my square is over here. So this is 0. I put the square over here, here circle, and here triangle. So what will happen over here now? Now it is 0, 0. So 0, 0, same dot. This is dot, dark dot is over here. Okay, then 1, sorry, 0, 1. 0 and 1 is over here. Look at here, this line is now transformed. X line is transformed to Y. So it is now here to here. So I put the square over here because this is the square. So this square is transformed over here. Then after I have negative 1 and 1. Negative 1 over here. That means this 1 here to here. Circle is transformed over here. And finally, I have negative 1, 2, negative 1, 0. That means my triangle is transformed. This is triangle actually. Triangle is transformed over here. So you can see my straight lines are transformed to straight lines, but in a different figures. And that is by the given nature of the matrix. Transforming the unit square by matrix multiplication. Transforming the unit square by matrix multiplication. So in previous figure, the unit square is again drawn along its transformation by A. Here the square did not simply slide to the left, nor did it flip across the y-axis. Rather, it would rotate anti-clockwise. Look at over here. This is like this. It was like this anti-clockwise. Here also we have the same thing, anti-clockwise. So it rotated anti-clockwise, or you can say counterclockwise, about the origin 90 degree. Rotation, the shape of the object does not change. This was square, this is again square. The shape of the object doesn't change. Square remained a square of the same size, right? Square remained. Again, it depends on the nature of the matrix, which matrix you are multiplying with, right? Okay, let's explore this thing. Let's explore this thing, this idea further by investigating two questions. Suppose we want to transform the Cartesian plane by rotating the plane counterclockwise 180 degree, not 90 degree, but 180 degree. How do we find the matrix which performs this transformation? Now see, in the previously, that means up to here, we were given one matrix, and after calculation A multiplied by B, after that we came to know that my square was transformed to 90 degree, right? My whole square starting with x-axis, then like this was transformed starting with y-axis, so 80 degree. Now the question is asked to you, do you figure it out the matrix which gives formation of a unit square by 180 degree? That means whatever 180 degree means, whatever the transforms you got over here, this one, the whole transformation that will be converted like this, 180. This is just 90 degree. Here to this here, and it's now 90 degree. But this will be gone like this. So it's not in second quadrant. 180 degree means it will be now in third quadrant. So which matrix will give you, means which transformation which will transform your unit square in the form of 180 degree. 180 degree means third. So that is now the question is asked in the reverse way. Second one, the transformation of a unit square really help in the understanding how the entire plane is transformed. The transformation of the unit square really help in understanding how the entire plane is transformed. Okay, let's answer these two questions one by one. Answer is actually yes. These two questions are closely related. See how the unit square was transformed. In particular, is there any correlation between where the vertices ended up and the matrix A? Vertices ended up, see, and the matrix A. That means the vertices means whenever you had these type of things, look at what these are the vertices. 0, 0, 0, 0, square, circle, and triangle. These are the vertices. So how what is the relationship between these vertices with the given matrix? That's what we are looking for in short. Okay, so first of all, the 0 vector never moved, because if you multiply any matrix by 0, again you will get 0. So 0 vector never moved. That makes sense because A times 0 vector equal to always A multiplied by 0 vector is always 0 null vector. The square corner never moved. The square corner, the corner corresponds to vector 1, 0. That is called a square corner because we put the square over there, right? Square, triangle, yeah. Square, then circle and triangle and like this. Okay. The square corner, the corner corresponds to vector 1, 0, is always transformed the unit vector to the vector in the first column of A. First column of A, right? First column of A. Again, the square vector corresponds to 1, 0, always transformed to a vector that is first column of A. First column of A. What was my first column of A? First column of A. Look at here, my first column of A was 0, 1. And 0, 1 that is here. So the square is always transformed to the first column. Okay, that means my square and then circle. Suppose I go for circle. Circle will transform to second column. Yes, look at here. The triangular corner, the corner corresponds to the vector 0, 1, is always transformed to the vector in the second column. 0, 1, that means it is here. 0, 1. 0, 1 is over here, sorry. 0, 0, 1, 0. What is this? 0, 0, 1, 0, right? And 0, 1 is over here. So this is my triangle. So this triangle that is transformed, this triangle is transformed to a second column of a vector. Look at here, that was my second column of a vector, second column of a vector. So this is my first column of a vector, that is this square. This triangle is nothing but the second column of a vector, like this. Second column of vector. The red dot corners always transform to the sum of the two columns vector A. The red dot corners. Red dot corners, that's the previous thing. Okay. The red dot corners is always transformed to the sum of the two column vectors of A. Okay, we'll see over here. We'll see here. We can understand these four parts by taking some matrix A like this. A multiplied by 0 is 0. So always you're going to get null vector. Second and 3 together. Suppose A is A, B, C, D. And suppose I take one matrix. E1 is 1, 0. Second one is 0, 1. 1 because this is the first point of my, or first vector of my square, unit square. Second vector for unit square. So first vector, that is 1, 0. Right, guys? First vector was 1, 0 square position. So 1, 0. That if you multiply this A by E1 or A and E1, you are going to get this multiplication is A and C. Look at here, A and C, first column. So 1, 0. Then E2 is equal to 0, 1. Right? E2 equal to 0, 1. So 1, 0, that is my unit vector like this. Again, guys, please pay attention here. 1, 0 is my unit vector like this along x-axis. 0, 1 is a vector, unit vector like this along my y-axis. This is my 0, 1 position, right? So this one that was transformed to my first column of a matrix A, and this one is this transformed to my second column of a matrix. Always keep in mind this thing, always. Okay, so AE1 is this one, 0, 1, that is E2. So A times E2 equal to B and D. B and D is my second column of vector. So always keep in mind this thing. By similar argument, we can demonstrate, one can demonstrate why the red dot corner is transformed to the sum of the columns of A. Sum of the columns of A, right? Sum of the columns of A, that means column of this one and column of this one, these two columns. If you add this one, A plus B, C plus D, like this. Revisit how the question, revisit the question, how do we find the matrix that perform a given transformation on the Cartesian plane? Okay. The answer follows from what we just did. Think about the given transformation and how it would transform the corners of the unit square. Make the first column of A the vector given to E1, and make the second column of A the vector that E2 goes. Right? That's what we saw. Let's now focus over here in this example. Find the matrix A that flips the Cartesian plane about the x-axis. That flip the Cartesian plane means xy plane about the x-axis, and then stretches the plane horizontally by a factor of 2. By a factor of 2. Read the question twice. It says that find the matrix A that flips the Cartesian plane about the x-axis. Cartesian plane is xy plane, and that plane is transformed, that flips to about the x-axis. Okay, and then stretches this plane horizontally by a vector, by a factor of 2. So we first consider, find the matrix A that flips the Cartesian plane about the x-axis. We first consider E1 because that is my first vector on the square. So flipping the plane across the x-axis does not change E1 at all, because this is just 1, 0 horizontal line. So if you flip this one, it remains the same. Horizontal line remains the same. So does not change your E1 at all. So stretching a plane horizontally, you can say, sends E1 to, if you stretch this one, if you have 0 to 1, 0 to 1, if you stretch like this by the same vector, same length, so it will be now 0 to 2. So 0 to 1, 0 to 1, then 0 to 2, like this. So your vector in that case, that would be 2, 0. So the first column of A is 2, 0 after stretching. Okay, let's go for the second one. Second one is E2 is 0, 1. 0, 1, there is a vector perpendicular to x-axis. Flipping the plane about x-axis sends E2 to the vector. If you flip this one, this will be that, because 0, 1, just try to look at like this. This is my x-axis, this is my y-axis, and this is my y-axis. And this point, my top finger, this one is 0, 1. This is 0, 1. This point is 0, 1 in Cartesian plane. If I flip it like this, so it will be over here. It will be over here. And this point is now 0, 1. This is x-axis, this is my y-axis. Below x-axis, this point is 0 and -1. Agree? So that's why flipping the plane about x-axis sends E2 to 0 and -1. And now we are stretching this one, 0 to -1. Stretching the plane horizontally. If you stretch this one now, that means you're going to cover my first vector. It was 0 to 1 because horizontal. We just stretched it, right? Flipping doesn't give us anything. So it is 0 to 1, and stretching, that was 0 to 2, means 2, 0 was the vector. 2, 0 was the vector. Now it is 0, 1. We flipped it. So it is 0, -1. Are you getting me? 0, -1. And now I'm stretching this one. 0, -, I'm stretching like this. If you stretch this one horizontally like this, if you stretch it, that means it's going to give you a rectangle. Am I right? It's going to give you a rectangle. So that's what it says over here, 0 to 1. So once you have, I repeat, first of all, you have your x-axis, your y-axis, 0 to 1. 0 to 1, that's my x-axis, 0 to 1, 0 to 1. There is no flip over here because there is a long x-axis. So it will remain the same. And you just stretch it by the same vector. So it is 0 to 2 now. So now you have 0, 0, 0, and 2, 0. These 2 points. Unit square or unit vector over here, that is 0, 1. This is 0 and this is 1, 0, 1. If you flip it along x-axis, so it will be now 0, -1. Now if you stretch this whole vector like this, with respect to your first vector, 2, 0. So it will give you 0, 0, 2, 0, -1, sorry, 2 and -1, and then 0 and -1. So you're going to get a rectangle. So second column of A is 0 and -1. Putting together, you're going to get A equal to 2, 0 and 0, 1. 2, 0 and 0 and -1. 2, 0 and 0 and -1. Look at here, guys. So find the matrix that flips the Cartesian plane about the x-axis and then, stretches the plane horizontally by a factor of 2. So horizontally by a factor of 2, that's why I went up to 2, right? Okay, so you're going to get this one. This is the matrix. So that's how you can fix your matrix with the given information. Good, guys. Some other figures are there. We'll see this thing one by one. And some examples. Article 5.3. This is Article 5.3. 5.1 and 2. They are just the repetition. So that's why we skip it. And we are we are doing Article 5.3. Okay. Some figures are here. See, if you flip this one, suppose this is M, flip it along x-axis. That means you are going to get, you are going to get this one, this W, right? This is unit length, but you have to stretch this one by up to 2 points. So this is 0 to 1, instead of 0 to 1, you have to stretch like this. It will go like this, 0 to 2, M will be like this and like this. But if you flip it, it will be a reverse case, 0 to 2, 0 to 2, and so M is converted to W like this. This corner is converted into this corner like this. This line will remain the same. So that's how this transformation goes. It's just the example, just some random example. Exercise problems are there. Look at here. They says that X and Y are given. Stretch X, Y, X plus Y, X minus Y on the same Cartesian axis. Did I provide you the practice test for this one? Last exam? Rolston, did I provide you the practice test for the last exam?
For the last one, yes, sir.
Yes or no?
Yeah, it was on Canvas for the last one.
It's on Canvas,
I
right?
haven't
Yeah,
checked
it's
this
on
one.
Canvas. Okay, yeah, that's what I just wanted to make sure. Okay, so here you can see here 1, -1, and 2. So 1, -1, and 2. So 1 is on x-axis. Actually, here it is three-dimensional plane, x, y, and z axis. So 1 and -1. Guys, please make sure how we draw this vector. I have to, you can't understand this thing over here. Just pay attention here on the page. Whenever you want to draw this some vector in 3 dimensions, first of all, draw three-dimensional picture like this, x, y, and z. Look at here. All of you can see my picture?
Sir.
Okay. Now, let me put some points. 1, 2, 3, 4, 5 on x-axis. 1, 2, 3, 4, and 5 on x-axis. Can you see here?
Yes, sir.
Put this type of points on all 3 axes. Please work with me. Initial 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. On Z also 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So you're going to get this type of curve, this type of three-dimensional Cartesian plane. Right? Now extend this line to x is extended to -x. Can I extend my x to -x by dotted line? Yes or no?
Yes, sir.
Can you see this dotted line, guys? All of you?
Yes, sir.
Okay. Same way you can extend your y-axis and z-axis. So -z, -y, and you can put your points over here to 1, 2, 3, 4, and 5. So -1, -2, -3, -4, and -5. Here also it is 1, 2, 3, 4, and 5. -1, -2, -3, -4, and -5. 1, 2, 3, 4, and 5. -1, -2, -3, -4, and -5. Look at here. This is called three-dimensional figure. Now, my first point, look at the screen. First vector x is equal to vector s is given to you 1, -1, and 2. Means 1 is on x-axis. So go for 1 on x-axis and -1 on y-axis. Look at here, guys. -1 on y-axis. So my 1 is over here. Look at here. 1 is over here on x-axis, and -y means dotted line. -y means dotted line, and 1 is over here. Try to make a rectangle over there. So, or square, something like this. So I'm going to make a rectangle or square like this. Look at here. Don't match these 2 points. Try to make a rectangle with these 2 points. Are you getting me? Are you getting me? Look at this square.
Yes, sir.
Okay. And then after I have, look at the screen. Here it is 1, -1, and 2. Then after I have 2. That means I have to go 2 points up because my z-axis is up. So I have to go 2 points up. So 1 and 2. So let me always put the dotted line. Don't use the straight line, please. So I just went 2 points up. Can you see the figure? I just went 2 points up. And whatever the dark red point I drew over here, from origin, that is my vector. So from origin, this is my vector x. Look at here. Whatever the x is given to you, that is the vector. So that's how you can draw the vector. Is it okay?
Yes, sir.
All of you convinced?
Sir.
All of you guys?
Yes, sir.
Yep.
Okay. Now my second vector, look at my vector y. My vector y is 2, 3, and 2. No negative. Okay, so 2 means I'm going to take first number from x, second from y, third from z. 2 and 3. 2 and 3 on y means I'm going to get, again, you have to make a square. Just look at my dotted line and you are getting some square over here. Can you see this slightly this dotted line and I made a rectangle here? Yes or no?
Yes, sir.
Okay, and then 2 points up. So this one, and then 2 points up. So if you go 2 points up, you are going to get 1 and 2. 2 points up. Can you see I just drew the dotted line 2 points up, and that is just above the negative x-axis, sorry, just above the y-axis. Can you see here, this point?
Yes, sir.
Okay, join this point from the origin. That will give you your another vector y. So this is my vector y. Can you see the vector y?
Yes, sir.
And compare this x and y vector with the vector on your screen. Compare whatever I drew over here, your vector x and vector y, with the vector on the screen. The vector on the screen, can you see can you observe this thing? That whatever I drew over here and whatever you can see on the screen, both are exactly parallel, exactly same?
Yes, sir.
I have not done anything so far about your x plus y or x minus y, whatever it may be, because we need to go to what? X plus y and x minus y2. Okay. So right now I just drew the vectors on the graph, three-dimensional graph, vector x and vector y, but not x plus y, not x minus y. Now I am going to do x plus y. So x plus y means add your vector. Your vector y is 2, 3, and 2. What is your x plus y? X plus y is addition, component wise addition. So 1 plus 2 is 3, negative 1 plus 3 is 2, 2 plus 2 is 4. Agree? That means my vector is 3, 2, and 4. And that's what I have over here. Look at here. 3, 2, and 4. Agree? And same way, if I want to draw my vector, find my vector x minus y, so subtract y from x. So 1 minus 2, that is equal to negative 1. Then negative 4, because negative 1, negative 3, and negative 2, negative 2 is 0. So negative 1, negative 4, and 0. At the most right side of the page, we have last two vectors, addition and subtraction. And now I would like to draw this addition and subtraction. So what we mean by the addition of two vectors? You know that addition of two vectors means, suppose I have one vector x is there, y is there, addition is exactly from the middle. Addition is from the middle. Addition is exactly from the middle. Just guys, give me 1 minute. Hey, hello. 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 Call. Hey guys, 2 minute mana ako, 2 minute join karo. Chalu rakho 1 minute. Can you hear me guys? Look at here.
Yes, sir.
Yes, sir.
Yeah. So what will happen here? This vector will go like this. Oh my gosh. This vector will go like this. Okay, and addition, this is 3, 2, and 4. 3, 2, and 4 will be like this. This is 3, 2, and 4. So vector 3 is here. 4 is on y-axis. If you make a rectangle like this, and then 4 point up. So 1, 2, 3, and 4 point up. So that will be over here. Sorry, x plus y, that will be over here. So 3, 2, and 4. So if you plot this one here, 3, 2, and 4. So let me draw this 3, 2, and 4. So 3 is here and 4 is here. So 3 and 4. 3, sorry, it is 3, 2, and 4. My bad. 3 and 2. 3 and 2. And then 4 up. So 1, 2, 3, and 4. So this is my vector. X plus y. Look at here, guys. This is my vector, x plus y. This is my x plus y. Agree?
Yes, sir.
Yes, sir.
Yeah. Okay, guys. So this way you can go for this three-dimensional vector 2. I think I covered everything of this chapter. You want me to start the new article today? Or I think this next article we can start next time, because we have just 5 minutes left out. So it's by